All right, so in your worksheet from last night, you guys had a question right at the end where you had to solve, or not solve, I should say, prove the cos of 2x equals, I think it was cos squared x minus sine squared x. Is that right?
Yeah.
Were you guys able to do that one?
Yep.
How did you do it, Jonathan?
So I kept the second part of the equation the same.
Yep.
The cos 2x, I split it into cos x plus x.
Ah.
And then I did the, what's it called? I'm trying to find the upper compound angle formula.
Okay.
So it would be cos x minus sine x. And then once you put them together, it's cos squared x minus sine squared x.
Awesome. So pretty straightforward proof after you understand this part, right? So that we can split 2x up into x plus x. So this is the idea. So from the compound angle formulas, we've kind of been working our way through the new list of identities that we have. Through those compound angle formulas, we can actually get what we call the double angle formulas as well. So we have the cosine double angle formula. The cosine double angle formula can be rearranged in a couple different ways with the Pythagorean identities. So we'll talk about that. But I want to solve the sine double angle formula as well before we talk about the cosine arrangements here. So along those same lines here, if we, I actually just realized that it's in example 2, so I didn't need to go back. Yeah, Fayak?
I have a question. So like, this basically, like, we're doing the same thing, like left side equals right side, but in this case, it's like double angle.
Yes. So same thing as always, but we're kind of working our way through the list of new identities and just proving that they're true. So along the same line of thinking, if I make 2x equal to x plus x here, I can actually use the sine compound angle formula in order to expand this. So what is the sine compound angle formula for addition?
Sine x cos x plus sine x cos x.
Okay, so this is going to expand out to, usually it's like sine x cos y plus cos x sine y, right? But we have x's for everything here. So it's going to be like sine x cos x plus cos x sine x. So I'm using this identity here, okay, the one at the bottom. And we're just replacing the y's with x's here. So we get sine x cos x sine x. Is sine x cos x the same thing as cos x sine x? 7 times 3, same thing as 3 times 7? Yeah. So I'm going to rate it as sine x cos x plus sine x cos x. So if I add one sine x cos x with another one sine x cos x, how many sine x cos x's do I have? I have 2. Perfect. And that's what we have on the right-hand side. I'm just showing that we can write cos x sine x as sine x cos x. What did you say? Did you say it's soft? Okay. I need to learn these new like terminology things. That's the only way I'll be cool, guys, so share your words with me. All right, I'm just going to recopy the one from above because I'm going to use a little bit of this to show you the other cosine double angle formulas. So we said with the one from the worksheet, we did x plus x, and then this expanded out into cos x from the cosine addition formula minus sine x. And that gives us cos squared x minus sine squared x. Also soft, Fayak? So we have left side equals right side. All right, so we've got a little bit more space here, and that's because there's actually, if you look at your sheet, there's actually 2 more cosine double angle formulas. So I'll just show you them here. So we have the sine double angle formula that we just proved, and then the cosine double angle formula that we just proved. But there's actually two more cosine double angle formulas. And they basically come from the first one, just plugging in the identities for cos squared x and sine squared x. So from the first identity, the following two follow. So if I take the cos squared, so we know now that the cos of 2x is equal to cos squared x minus sine squared x. If I take cos squared x and I enter in its identity, which is 1 minus sine squared x, so you guys remember from the rearranged Pythagorean identity that cos squared x is actually equal to 1 minus sine squared x. Okay? How many sine squared x's do I have here? I have 2. I have negative 2, actually, of them. So negative 2 sine squared x. So we have one more identity, which says that cos of 2x must also be equal to 1 minus sine squared x. And then I have another identity that I can get from this original identity by plugging in the sine squared x Pythagorean identity. So what's the Pythagorean identity that we can replace sine squared x with? We learned this back in grade 11. We reviewed it in the first lesson as well. What's the Pythagorean identity for sine squared x? Come on, I know somebody knows it.
It'll be 1 minus cos.
1 minus cos squared x, yeah. And then I'll distribute the negative. And we have 2 cos squared x's, and that will be subtract 1. So here's my extra 2 cosine double angle formulas. Okay, sometimes with the cosine double angle formulas, you need to kind of pick, and you might need to guess and check which ones work in your trig identity that you're trying to prove. So sometimes one of them may not lead you along the right path, and you can try another one. You could always technically get to the thing that you need through any of them just by using the Pythagorean identities. But if something's not working for you, if you've chosen one of them, try a different one and then recheck if that's getting you to where you need to go. Okay, so those are our extra 2 cosine double angle formulas.
So would we need both?
I mean, I'm going to give you this whole sheet anyways, so you'll have all of them.
I know what I'm saying, like, if you have to answer this question, would any of them be fine?
Yeah, so like I said, some of them might work and some of them might not, depending on where you need to go for your right-hand side as you're proving a trig identity. So you might need to try one and then see if it works, and then if it doesn't, yeah, if you can get to where you need to go and you've proven it, that's fine. Okay, so there's all of our double angle formulas. The tan double angle formula, you can basically just prove with the tan addition formula, similar to how we proved sine of 2x and cos of 2x with the cosine and sine addition formulas. So if I were to go to my identity sheet here and use the tan addition formula and plug in tan x plus tan x minus 1 minus tan x times tan x, I'm going to get tan x plus tan x is 2 tan x on the top minus over 1 minus tan squared x. So that's where this guy comes from here. Okay? Okay, so we're going to apply these in some questions with exact values. So simplify each of the following expressions, then evaluate. So 2 sine something times cos of the same something. Where does this come from? Does any pattern up here work for that?
The first.
Yeah, so we have 2 sine cos. So how can I write this if I'm going from here back into this? Well, I'm simplifying this into one single expression, right? So I'm taking what I have here, and I'm technically going backwards to write it in this format here. Yeah, so sine, and then our x here is like pi over 12. So it would be like 2 times pi over 12. And 2 pi over 12 is pi over 6. So can we evaluate this exactly now? We can. And it is 1 over 2, that's right. Good job.
What happened to the cosine?
So we're using the identity above here. So we know that the sine of 2x is equal to sine x cos x. So I'm putting this back into the sine double angle format. So sine of 2x.
When it says 2 sine x cos x, does that mean sine x cos x plus cos x sine x? Like this is double?
Yeah, sine x cos x plus itself. Yeah. Okay. Does this pattern fit into anything you see above with your formulas? Into what? Into the last one here. So this, we're going to go backwards into this format. So how would we write it? Tan 2 pi over 8, which actually reduces to the tan of pi over 4. So can we find tan of pi over 4? Jonathan? It is 1. So we get, like, when we do opposite over adjacent, we get 1 over 1, which is 1. Perfect. Any questions for that one?
So we only take the first term, right? The 10. Let's say if we're doing 10 and we only take the 2 10, right? We don't mess with the 1 minus 10 stuff.
So this whole pattern right here, we know is equal to the tan of 2x.
Oh.
So we're doing the tan of 2, and this is like our x, right? Like our angles that are here are like our x's there. No problem. Okay. If cos of theta equals negative 3 over 5, and theta is between 0 and 2 pi, so it's just in that first rotation, determine the value of cos 2 theta and sine 2 theta. Just as a little note, to find sine of 2 theta, we need to find sine using the cosine ratio that's given to us. So we're going to need, because the sine of 2 theta is equal to 2 sine theta cos theta, or sine 2x cos x, we also need from this to be able to find the sine of that same theta. Since the original cosine is negative, we need to consider both quadrants that our answer could possibly be in. So if cosine is negative, what are our options for the quadrants that that could be in?
The left 2 quadrants.
Yes. Could be in tan or sine. Does anyone know what numbers of those are those quadrants?
Oh, yeah.
2 and 3. Yeah. Okay, so we need to consider both possible scenarios. Now, the only thing that's going to change, the ratio is not going to change, but sine is positive in that second quadrant, but it's negative in the tan quadrant. So we just need to consider both possible options for where that angle could be. Yeah, Fayek?
C was 1. Wasn't it 1?
No, the all quadrant is, it starts in the top right and moves counterclockwise. Okay, so here's the question. Let's just pretend that this is in the second quadrant for now. If cosine of theta, this is going to be our reference angle theta, is equal to negative 3 over 5, that tells me the adjacent side and the radius of the circle. I need to find y. How can I find y? Alexandra?
X squared plus y squared equals r squared.
Nice. Okay. So I'm getting 4 here for this. Now, I want to consider actually if I have a triangle down here that has the same reference angle and the same radius, I want to consider the y's in both of these quadrants. So which one has the positive 4 and which one has the negative 4?
Positive goes to sine, negative goes to tan.
Yeah, so up here is positive 4 and down here is negative 4. So the only thing that really changes, like I'm going to get the same y value, but the one in the top quadrant, obviously if I go up on the y-axis, I have positive 4. And if I go down on the y-axis, I have negative 4. So when I plug this in here, I will do the option in quadrant 2, and then I'll also do the option in quadrant 3. So what is sine of theta in quadrant 2? What is sine of theta in quadrant 2?
4 over 5.
Positive 4 over 5. And cosine of theta we already know is negative 3 over 5. So we're going to get negative 24 over 25. So this would be if we're in quadrant 2, right? If we're in quadrant 3, we have a different scenario. We have 2 times negative 4 over 5 times negative 3 over 5. So the only thing that changes is we actually just get a positive 24 over 5, or 24 over 25, and this would be the answer for quadrant 3. Okay, this also asks us to find the cos of 2 theta. You should be able to use any one of the 3 cosine double angle formulas in order to find this. I usually just use the first one, but you should get the same answer as us if you use any of them. So cos squared theta means cos theta times cos theta, right? So I already know that cos theta is negative 3 over 5. So I essentially have negative 3 over 5 squared if I have cos squared theta. Cos theta times cos theta. And same thing for sine. So let's just say it's 4 over 5. Is it going to matter if it's positive 4 or negative 4 over 5 for this one? If I'm squaring it? It doesn't matter, right? Because when I square it, a positive will remain positive and a negative will become positive. So this one will only have one single answer. I'm going to get 9 over 25 minus 16 over 25. And we'll end up with negative 7 over 25. Okay, and that would be for quadrant 2 and 3. Okay, in other scenarios, it may actually tell you what quadrant you're in, but if it doesn't tell you and it just tells you you're between like 0 and 2 pi, like just in that rotation, you'll have to consider both possible answers using the cast rule. Are there any questions on this one? We're okay? Okay, so as I said, sometimes we will be told the quadrant. So in this case, we get that tan of theta is equal to negative 1 over 4, and it's between 3 pi and 2 pi. Which quadrant is this? It's in quadrant 4, or the cosine quadrant, right? So it should make sense that tan is negative in the cosine quadrant, right? If you get something that doesn't make sense based on the cast rule, that shouldn't happen, right? Once we do double angles, though, the cast rule doesn't apply once I do like the cos of 2 theta, right? So just because something is in, let's say, the sine quadrant, in quadrant 2, it doesn't mean that the sine of 2 theta is going to be positive. Okay, it only means the sine of theta will be positive in that quadrant. So just watch out for that. Okay, so I have tan in the 4th quadrant, or the cosine quadrant, and it tells me, so we'll make our triangle here, tells me that tan is equal to -1/4. So how do I know whether it's the x or the y that's negative here?
It's the y, it's going down.
Yeah, take a look, use your common sense. If I'm going right on the x-axis, x must be the positive one, which is 4, the opposite, or the adjacent, and y must be the negative. So I need to find radius if I'm going to find the cos of 2 theta. So we can use Pythagorean theorem to help us with that. And the radius is always positive, so only x and y can be either positive or negative. If I'm finding radius and I'm isolating there, it's like the radius of a circle, right? We're talking about points on the outside of a circle. So radius, you don't need to consider positive and negative options. That one's always positive. It's only if you're solving for x and y that you need to consider positive and negative options. So our radius will be √17. So if cos of 2 theta is equal to the identity cos squared theta minus sine squared theta, okay, I first need to know, in order to solve that, what cos theta is equal to and what sine theta is equal to. Can someone help us with those? For cosine?
Yeah.
4 over √17, and for sine? -1/√17. Awesome. Okay, so we're going to plug these in then. So it'll be 4 over √17 squared, and then -1/√17 squared. Okay, you square a fraction, just so we're all on the same page here, just square the numerator and square the denominator if you need to square a fraction. So I'm going to square 4, and I'm going to square √17, which just leaves me with 17. Yeah. And then -1 squared is 1, and √17 squared is 17. Pardon?
Oh, never mind, minus.
Yeah, if it were plus, it would be 17/17, you're right. How can I check my answer? Yeah, if I plug this in,
What did we just solve for?
we solve for cos of 2 theta. Actually, yeah, I don't think we can actually check that way. We didn't solve for theta, though.
Solve for cos 2 theta.
Yeah. So what you could do is you can actually, that's cos of theta. This is cos of 2 theta. Yeah. So what I would say, you can't plug this back into an original theta because we didn't actually solve for the angle itself. Well, if you wanted to solve for theta, you could. But my suggestion would be, you have 3 cosine double angle formulas. You could plug it into another one and just check to see that you get out 15/17 as well. Okay, or the other option could be, if you want to actually solve for the angle, you could do like the inverse and then check to see that the cos of that angle actually gives you 15/17. That's another option. Okay.